This is a demonstration of a system monitor program for the CPUville 8-bit computer processor. This is the setup I'll be using for this demonstration. These three boards are the 8-bit processor, the arithmetic logic unit or ALU, the data path with the registers and multiplexers, and the control logic board is here. They're connected. I don't have the register display on because this demonstration uses the processor running at full speed, and so the register display is just a blur and there's not much information you get from it. The processor is connected to the Z80 computer system through the Z80 slot and this adapter, and I have the serial interface board connected so that I can connect the computer to the personal computer and interact with it using the keyboard and display on the personal computer using a terminal emulation program. The system monitor program has been written in the assembly language for this homemade processor, assembled with the TASM assembly program, and placed into the EEPROM here. The code had to fit in the 2K space allowed for it in this system. There's also 2K RAM that can be used for programs. The first 256 bytes of the RAM, however, is set aside for variables and input line buffer for use by the system monitor program. I'm going to use the real-term terminal emulation program in Windows to communicate with the computer that uses the 8-bit processor. This is the real-term window, and I'm going to set it up to communicate with the 8-bit processor computer system. We'll pick the ANSI display and display 24 rows. The baud rate of the port has to be set to 9600, and it will be no parity, 8 data bits, 1 stop bit. Finally, we click in the screen to allow the emulator to accept keyboard input and send it over the serial port. Now that we have the terminal emulation set up, I'll reach over and take the computer out of reset. You can see it displays a greeting and a prompt that shows the 5 different options for routines that the system monitor can perform. So the first routine, restart, just cycles back to a warm restart of the system monitor program. The dump routine allows you to view memory. I will display the first part of the user memory, which is at 0900 in hexadecimal. And here it displays 256 bytes as hexadecimal pairs. And this is just the garbage that's in the memory when the computer is powered up. The next thing I'll demonstrate is the load routine. We can use this to load data into the memory from the keyboard as hexadecimal bytes. So we'll load this area of memory, starts at 0900, and I'll just put in a bunch of zeros to clear it out. And now we can look at that area of memory. And now it shows the zeros that we put into it. I've written a brief program to demonstrate the run routine. this is a listing of the program. The assembly language is over here, and this I run through the TASM assembler program using an assembler table that's specific for the new processor, and it generates the object code, which is here, machine code, and puts it in a list file that also has the memory locations that I've assembled it to. So the code for the program is these 7 bytes, 10C31800 139800, and it performs a very simple function. It just loads the hexadecimal bit pattern C3 into the accumulator and outputs it onto the output port LEDs. Then it returns to the system monitor warm start address. Now I'll use the load routine to put these bytes of program into the RAM, and again we'll put them in at 0900. And the bytes are 10C3 1800 139800. Now we can examine this area of memory with the dump command, and we see the bytes of the machine code here in the RAM at location 0900 and after. Now we can run this program using the run routine, and we'll cause a jump to the address that we've listed. The run routine finishes and returns to the system monitor warm start, and you can now see on the computer LED readout that that bit pattern C3 is present, so that we know the program ran correctly. Now, as a simple demonstration of changing a byte in the program, we can change the output pattern from C3 to something else using the load routine. So the output pattern is present in memory at 0901, so we will change 0901, and we can change it to something else, say 3C. Now if we look at the memory, we can see that the program contents have been changed. Now if we run the altered program, you can see the bit pattern 3C on the output LEDs now, indicating that the program ran correctly. The last part of the demonstration, I'll show you the binary load or BLOAD routine. This uses the real-term capability for sending a file across serial port, and you can load raw binary data into the 8-bit computer using this command. The send tab of real-term allows us to do this. So I've set up the send tab to send a file named RAM test, which is the same program that I ran by typing in the hexadecimal characters. So the assembler has put out a binary file of the same data, and that's what we'll send to the computer. So we need to start the binary load command, and the address, I'll just put it in say 0920 just to put it on a different line of memory. And we have to tell the system monitor how long the file is. It doesn't have any other way to know. It's just getting bytes coming over the serial interface. So this particular file has 7 bytes. So now it's ready to transfer, and we hit the Send File button. And after the 7 bytes are received, the system monitor returns to the prompt line. We can verify that the program is in memory, of course, by using the dump command and looking at the block of memory that we've been dealing with. And you can see there the bytes of the binary file that we loaded. Notice that it contains the original C3 bit pattern that was in the original program that we typed in. So now we'll go ahead and run the program. It's at address 0920, and after running we return to the prompt, and you can see by looking at the LEDs on the computer that the C3 pattern was placed there by the program, indicating that it ran correctly. This concludes the demonstration of the system monitor program for the CPUville 8-bit processor connected to the Z80 system. Using the system monitor, you can write programs, load them, test them, debug them, and eventually work up to more sophisticated software such as an operating system. Thanks for watching.